Hello, my name is Chen Shuning. I will be presenting a report on my recent deep learning project. In this project, I use Chinese English test data provided by NIST to train a simple Chinese English translation system. Through this practice, I aimed to learn the specific details of the CIP2 model and understand the base technologies of machine translation. This report is divided into 6 parts. Introduction to the 626 BizNet model, replacing the RR model with GRU and LSTM, using a bidirectional encoder, implementing the extension mechanism, hyperparameter tuning, adjusting the teacher floating probability. First, I will introduce the baseline model used in this study. The experiment utilized the seek-to-seek model, which consists of 2 parts, an encoder and a decoder, both of which are reads. The encoder converts the text into a tensor as input and outputs the final hidden state of the run layer. The decoder is similar but includes an additional fully connected layer with softmax activation to define the probability distribution of the next word in the translation. During training, 2 techniques were employed. Teacher forcer, which consistently provides the correct answer, a scheduled sampling, which gradually allows the model to make its own predictions. Now let's look at the results. From the loss graph, the lowest value reached was 3.9. Comparing the translation outcomes, the original code showed almost no effective translation. I believe the poor performance of the run in this translation path is mainly due to its difficulty in capturing long-term dependencies, susceptibility to gradient issues, limited memory capacity, and lack of parallelism. To improve performance, I replaced the RNN with GRU and LSTM for experimentation. First, let's examine the results of replacing the original RNN with GRU. The loss decreased significantly more, and the translation quality improved compared to the original RNN model. For example, the sentence "Why can't I learn English well?" was translated by the GRU model as "Why as I speak English?" while the RNN model translated it as "Why do you want to go?" Although neither is entirely correct, the GRU model's translation is much closer to the correct answer, whereas the RNN's translation is largely irrelevant. Therefore, replacing the RNN with GRU in this experiment led to a noticeable improvement. Next, let's look at the results with LSTM. From the loss graph, there was a significantly greater decrease compared to the original RNN, and the translation quality also improved. For instance, the sentence "What's the weather like today?" was translated by the LSTM model as "What's the weather today?" while the RNN model translated it as "What is you?" 2. Clearly, the LSTM translation is completely correct, whereas the RNN's translation is entirely off. This, replacing the RNN with LSTM, resulted in a significant improvement. In this text translation task, GRU and LSTM performed significantly better than the traditional RNN for several reasons. GRU and LSTM introduce gating mechanisms that better handle dependencies in long sentences, capturing grammatical and semantic information. They effectively mitigate the vanishing gradient problem, allowing the model to learn more steadily and deeply during training. GRU and LSTM can flexibly handle information across different time spans, adapting to sentences of varying lengths. They have a stronger memory capacity for important information, enabling more precise understanding and translation of long texts. Overall, by improving the structure, GRU and LSTM address the shortcomings of RNN, this performing excellently in translation tasks. To further enhance performance, I used a bidirectional encoder to obtain a better representation of the source language. First, let's look at the results with the bidirectional GRU. From the loss graph, the loss decreased significantly more than with the unidirectional GRU, reaching a minimum of 2.8. Additionally, the translation quality was notably better than that of the unidirectional GRU. For example, the sentence "I can't help you anymore" was translated as "I can't help you" with the bidirectional GRU, whereas the unidirectional GRU translated it as "I can't you. This shows a clear improvement. Next, examining the results with the bidirectional LSTM, the loss decreased more compared to the unidirectional LSTM, reaching a minimum of 2.95. The translation quality was also slightly better than that of the unidirectional LSTM. For instance, the sentence "He can't speak French or English" was translated by the unidirectional LSTM as "He can't speak English," while the bidirectional LSTM translated it as "He can't speak French English." Although both translations deviate from the actual meaning, the bidirectional LSTM's translation is better because it includes both French and English, whereas the unidirectional LSTM only mentions English. In this text translation experiment, the bidirectional encoder performed better than the unidirectional encoder for several reasons. Bidirectional context: it allows the encoder to see both preceding and following content of a word, providing a more complete context, particularly suitable for handling long-distance dependencies. Improved information transfer by encoding and merging forward and backward information. The model integrates important features from different directions, leading to a more accurate understanding of the sentence. Unidirectional encoders can only see preceding text and may miss important following information, whereas bidirectional encoders address this through bidirectional processing. Overall, the bidirectional encoder demonstrates clear advantages in text understanding and translation tasks. Next, I implemented the attention mechanism to further improve performance. In this enhancement, I use GRU as the base unit for both the encoder and decoder, primarily because GRU has a simpler structure with fewer parameters, which improves computational efficiency and is suitable for handling long sequence data. For the attention mechanism, I chose .product attention due to its simplicity and speed, which helps the model dynamically focus on the most relevant information in the source sentence during translation. Overall, combining TRU with .product attention ensures efficient model operation while improving translation quality. First, from the loss graph, the final loss value with the attention mechanism is slightly lower than that without it, by about 0.1. In terms of actual translation quality, the model with attention performs better. For example, the sentence "What's the weather like today?" was translated by the GRU without attention as "How's the weather today?" Or with attention, it was translated as "What's the weather like today?" which is completely correct. Another example is the sentence "She likes eating strawberry-flavored yogurt." The standard GRU translated it as "She likes to eat sushi," meaning she likes to eat sushi, whereas the GRU with attention translated it as "She likes to drink milk," meaning she likes to drink milk. Clearly, the translation with the attention mechanism is closer to the actual meaning. Next is hyperparameter tuning. Here, I tuned hyperparameters including the type of attention, the number of neural network layers, the dropout probability, and the learning rate. I found that the best performance was achieved with a learning rate of 0.0005, 2 layers, additive attention, and a dropout probability of 0.05. Finally, I conducted comparative experiments on the teacher forcing probability. The probabilities tested was
0.5, 0.7, and 1.
From the loss graph, the lowest loss was achieved when the teacher forcing probability was 1. Finally, I integrated all the optimal hyperparameters from the previous steps to train the model. Both the loss and the translation results were significantly better than before, representing the best translation quality I could achieve. For example, the sentence "Tom isn't a good driver" was translated as "Tom isn't a good swimmer," meaning Tom is not a good swimmer, which is very close to the correct answer. In previous iterations, this translation was largely incorrect, and similar improvements were observed in other sentences. Overall, the hyperparameter tuning was relatively successful, enhancing the translation quality. My presentation is concluded. Thank you.